about our definite integrals. So if we recall when we started talking about our derivative last semester, we discussed the concepts of position, velocity, and acceleration. And we know that velocity is the change in position over change in time. And this is a formula we learned a long time ago. Distance is rate times time. And we solve that for rate. To get our rate is the distance we travel over our time. So we're going to continue to explore velocity with our well-known formula, distance equals rate times time. So we have our first scenario. A train moves along a track at a steady 75 miles per hour from 7 a.m. to 9 a.m. What is the total distance traveled by the train? So we can do this the old-fashioned way. Distance equals rate, 75 miles per hour times 2 hours. Our hours divide out, and we get 150 miles. Now we can represent a graph, and we're going to do time versus velocity. So here is the time, here is the velocity, 25, 50, 75, 100. And then we've got 7 a.m., 8 a.m., 9 a.m. So we're traveling at a constant rate between 7 and 9 a.m. Now, if we use our area model, we would have our 75 times our 2, and our area would be 150. And so it does, this 150 does match our original calculation. And why did this happen? Because the velocity is constant, not variable. And if we wanted to take and use an integral to represent the situation, we would take the definite integral from 7 to 9 of 75. And probably put dt because we're talking about time here. Okay, now we're going to change it up a little bit. We have a train moving along a track at a variable rate from 7 a.m. to 9 a.m. What is the total distance traveled by the train? Could we use the formula distance equals rate times time to answer this question? Then we have the time versus the train's velocity from 7 a.m. to 9 a.m., where our point A would be 7 a.m. and our point B would be 9 a.m. If we calculated the area here, would that represent the distance traveled? The answer is yes. And why? Because this is the same concept of the area between the curve and the x-axis. And here we would write the integral from a to b of v of t dt. So here we wouldn't use an area model. We would use our definition of a definite integral as the antiderivative at the upper limit minus the antiderivative at the lower limit. But if you recall, the antiderivative of velocity is really our position function. All right, so here's a couple of examples. We're going to first write a definite integral to model the situation, and then we'll go ahead and evaluate these definite integrals. So we have a pool pump that filters at a rate of 42.2 gallons per minute from the time that it is turned on at 1 p.m. until it's turned off at 5 p.m. Determine the total number of gallons filtered. So we start at 1 p.m. end at 5 p.m. and filter at a rate of 42.2 gallons per minute. So I am collecting the rate over time. We know how to evaluate this using one of our integral rules. Upper limit minus lower limit times our constant, and this would give us per minute. I have to make an adjustment here. I'm doing it per hour, but it's gallons per minute, and these are in hours, so I need to amp this up. There are 60 minutes in each hour, dt. Now we would have upper limit minus lower limit times that integrand, which here is just a constant. So that would be 10,128 gallons. All right, our next example, we have a 1 MW power plant that generates 900 kilowatt hours of power between 4 and 6 a.m. However, at 6 a.m., the plant shuts down for maintenance until 9 a.m. From 10 a.m. until noon, the power plant generates 1,000 kilowatt hours, so that maintenance was fruitful. Determine the total number of kilowatt hours the power plant generated from 4 a.m. to noon. Here we would have to use another one of those rules. We went 4 to 6 at 900 kilowatts per hour. Okay, we did nothing from 6 until 9. We don't have to write this one, but it's showing the Starbucks rule. And then we went from 9 to 10. Down from 6 to 9. And then from 9 to 10, doesn't look like it did anything either. But then from 10 a.m. to noon, we have 1,000 kilowatts per hour. So then we would take upper limit minus lower limit times our integrand. This is going to be 0, 0. Upper limit minus lower limit times our integrand. And we would get 3,800 kilowatts hours produced. All right, and the next little topic in this lesson is looking at our integrand. And we want to take a long look at this one because we have a theorem in our textbook that states that all continuous functions are integrable. Well, first we'll look at this function. Is this function continuous? And we would have to say no, not over all real numbers. Okay, where do we have a discontinuity? At x equals 2, and we would call this a removable or point discontinuity. And so I still would argue that we can integrate this function from 0 to 3, even though that 2 is a discontinuity. And the rule that we need to use is the Starbucks rule, the one we learned or used in the previous example. I'm going to integrate from a to b of f of x dx, and then from b to c of f of x dx, and that will get me the total amount from a to c of f of x dx. So our model will look like 0 to 2 x squared minus 4 over x minus 2 dx, and 2 to 3 x squared minus 4 over x minus 2 dx. And then we're going to use our area model. So we know that this would just simplify to x plus 2. So here's our y-intercept of 2, and then we'd have our slope of 1 over 1 up 1 over 1 up 1. So here's our first part, our integral from 0 to 2, and then we're going to pick up where we left off. Go over 1 up 1, and here's our part from 2 to 3. And here we have two separate trapezoids. My first trapezoid has a base, or excuse me, a height of 2, and one base that is 2, and the other base that's 4. And then we would add that to this other trapezoid, which has a height of 1, and a base of 4, and a base of 5. So this would be 6 plus 9 halves, or 10 and a half. So the integral from 0 to 3 does have the value of 10 and a half. Okay, we'll do another one like this. Here we see that we cannot allow x to equal 0. So we are going to integrate from -1 to 0. And then pick back up and go from 0 to 2. This, let's graph it out. So I'd have -1, absolute value +1, divided by a -1. That would also be a -1. And that's what I equal this whole entire time until I get here. At 0, I don't exist, as I can't allow to be 0. But then at 1, 1 divided by 1 is 1. 2 divided by 2 is 2. And now my two areas, this one is going to be a square, and this one is a rectangle. My first area is 1 by -1, because that area is underneath the x-axis. And my second area is a 2 by 1 by -1 plus 2, or +1. So the value of this integral is positive 1.